Hello. Due to popular demand, I'm going to start making a recorded version of the tutorials just to upload on my YouTube channel, just in case any students want to see the tutorial again or kind of highlight on some of the bits that they may have been stuck on when we went through it in person. This is not intended to be a substitution for the in-person tutorials because you won't have any interactivity, and I'll just pretty much go straight to the point without really asking the questions because obviously there's no students to talk to. And yeah, let's get into the first one. So tutorial 8. Prove that all linear functions f from R to R can be written as fx is equal to ax for some a and r. So when you first look at something like this that you're asked to prove, you really need to ask, what is the thing I know and what is the thing I want to show? In this case, the thing that I know is that f is going to be a linear function from R into R. Okay, so this is the information that I know. Okay, and what I want to show from here is that it can have this form where a is just a real number. So first thing you really need to do is figure out what a linear function is. Well, in the text we are told that the definition of a linear function is a function such that for all values of s and t that are in the real numbers, and for all values of vectors, say x and y, that are in the domain of the function, so in this case the domain will be this r, then f evaluated at sx plus ty is the same thing as this linear combination of s f of x plus t f of y. Okay, so this is the definition that we're using as our starting point for this question. Okay, so from here, it turns out that we don't actually need all of this for this question. In particular, it's sufficient to just look at this situation where t is equal to 0. So in that case, this term goes away and this term goes away. So from here, you can kind of notice that this s times f of x looks kind of similar to this ax. It's not the same, but that's some justification for why I could potentially use this situation where t is equal to 0. So let's go into the proof. So solution. Since f is linear, for all x in s and r, f of xs is equal to sf of x. So from here, this is just the statement that this over here is true. Okay, so now let's just explore this a bit. I really want this f of x thing to just be x, right? And I really want the s thing just to be a, or maybe vice versa, something like that. So let's just explore and plug in some values and see if I can get a real number a from this expression here. Well, 1's a real number, right? So I could simply say let x be equal to 1. And in this situation, this expression here simply becomes f of s times 1 is equal to s times f of 1. Okay, so this kind of begs the question, what is f of 1? Well, since f is a function from R to R, and 1 is a real number, f of 1 just has to be an element of this thing here, so f of 1 is some real number. I can give it any name I possibly want, so let's just call it a, because I want to get f of x to look like a times x, so a is a good name here. Okay, so now I can just notice, hey, f of x, well, that's the same thing as f of x times 1, and since x is just a real number in this case, I can split this up to say that's x times f of 1. F of 1, I know that that thing's just a real number, and I call it a, so this gives me that all functions that are linear from R to R can be written in the form a times x. Okay, so why talk about this particular problem here? Well, we're familiar with functions from R to R, and it turns out that just examining linear functions from R to R can tell us quite a bit of the ideas behind what's happening when we start examining linear functions from, say, Rn to Rm. Okay, so let's kind of examine what's happening here with this representation of this linear function. Well, a few things to note. One, instead of talking about f of x is equal to ax, I can instead just purely talk about this matrix A, right? So here the name of the function doesn't really substantially change anything mathematically, and the name of the variable doesn't really change anything, right? I could call it X, I could call it Y, I could call it Z, Bob, whatever I want. So the only thing that really is distinct here is A. So this is the idea behind a matrix of a linear transform. If for all linear transforms I can just talk about the matrix instead of talking about the linear transform, that's kind of useful because I know a lot of things about matrices, right? I can compute null spaces, column spaces, inverses, all this good stuff, but I don't necessarily know how to do that for linear functions at the current time at least. Okay, so I can use stuff that I know about A to be able to talk about the linear function if there's this connection, and there is. So the next thing to note is f inverse of x might not exist, right? So previously we noted that if I talk about matrices from say Rn to Rn, it might not be invertible. And one way to think about why matrices aren't necessarily invertible is to use this analogy up here. So if I draw my xy axes like this, then I can draw different lines that look like ax for various values of a. If a is positive, it'll look maybe something like this. If a is negative, it'll look something maybe like this, where it goes through the origin through the power of post-processing. So clearly these two lines would denote invertible functions, but if I draw this line where a is 0, this isn't invertible since everything gets mapped to the same thing. I can't undo what f does. So at least in this context, you can see why matrices might not be invertible, because if f of x is 0, then the matrix in this case was 0, and there the inverse would not exist. So for higher dimensions again, A doesn't necessarily have to be the 0 matrix for it to be non-invertible. We covered some examples of that previously. Okay, so beyond here, you can notice, hey, if f is a function from R to R, and it's a linear function, then f of x is equal to b of x, right? So now let's just look at function composition just briefly to get an idea of how that relates to matrix multiplication. Well, f of g of x is just f of plug in whatever g of x is, so bx. Now f is a times x, so f of b times x will be a times b times x with those parentheses. Now you can notice in the real numbers, I can swap the order of these parentheses like that. Okay, this is matrix multiplication. That means that matrix multiplication is function composition. I put is here in quotes because they're different mechanically, right? But if I have two linear functions and I compose them, there are matrices that I could use to represent that function composition as matrix multiplication. We'll get into this in more detail when we talk about composition later.
Later.
And the next thing to know is that matrix multiplication need not be commutative because generally speaking, function composition isn't commutative. It is for linear functions from R to R since real numbers are commutative, but in general, that's not the case. Okay, let's look at the next example. So consider a linear function f from R2 to R2 defined by f of x1, x2 is given by these two pairs here. Okay, given this, I can ask for some information. First, what's the domain of f? What's the standard matrix f for f? And use the standard matrix to evaluate f at the point pi e. Okay, so what's the domain of f? Well, generally speaking, the domain will just be the thing over here, given that you can actually evaluate the function. So for this course, that really won't be an issue for most problems, but just for completion, for any x in R2, I can compute f of x, therefore the domain of f is R2. So why do I care about the domain of f? Well, the way that I find the standard matrix depends on what the domain of f is. Previously, in the case where I had a function from R to R, the domain was just R, so to compute the matrix, all I needed to do was compute f of 1. Well, to compute the standard matrix. So here, to compute the standard matrix f, since the domain is R2, I need to use the standard bases for R2 to be able to compute the matrix for f. So from here, how do I find the standard matrix? Well, recall, since this is the domain, the standard matrix is simply f of e2, f of e1, f of e2. Okay, so just for completion, if the domain of f was R3. So for instance, if f went from R3 into something, it really doesn't matter what it goes into here. Then to compute the standard matrix, I would have to evaluate f at the standard bases for R3. So f of E1, comma f of E2, comma f of E3. Okay, so yeah, that's why you care to know what the domain is. Okay, so now the next thing I need to know is how do I compute these quantities? Well, here, E1, that's just the vector 1, 0, right? So f of E1, this is just going to be the same thing of f of 1, comma 0. Okay, and when I do this, it's just like computing f evaluated at a point in the old days, except for now I have two numbers to plug in. So from here, I would plug in my 0 in for x2, so I get 2 times 0, and then I would plug in my 1 and 0 to get a 1 minus 0. And this, of course, is just 0, comma 1. So then I take this point and I turn it into a column vector, and that's what my first column will be. Now I just repeat the same process with the point 1, 0. So just briefly, f of 0, 1. F of 0, 1, that will simply be 2, right? 2 times x2. If x2 is 1, that's what I get. And if I plug in 0, 1 into here, it'll get minus 1. So that will be my second term here. Okay, so beyond here, I want to use the matrix F to evaluate f at pi, comma e. Well, in order to do this, we need to kind of use the fact that now that I have this matrix representation, I can say f of x1, comma x2. Well, this thing will simply be equal to the matrix for f multiplied by this vector that has x1 and x2. Okay, so from here, I just do a straightforward computation. So the point that I care about is pi e, so I can evaluate this. Well, that's the same as this matrix multiplication, and it's pretty straightforward. Here I get 0 times pi plus 2 times e, so 2e, pi times 1 minus 1 times e, so pi minus e. So thus my point would simply be this thing here, and evidently I didn't fix it on this version of my slides. So we just need a comma between that, and yeah. Okay, so that's how to do this question. So let's go on to the next one. Prove that this is a nonlinear transform. So if I go back to the definition of linearity, I know something is linear if this thing up here is true, where I remove this stuff in red. Like that. Okay, so if I want something to be not linear, then this needs to be a false statement. So how do I make this a false statement? Well, I just need to show that there is some s and t in R and some vectors x and y in whatever space I care about. So here is going to be R3, such that this thing is not true. So explicitly from the slides, I need to show that there's this guy such that that doesn't hold. Okay, so how do we go about doing this? Well, I have 4 things to choose from that I need to pick, right? And it turns out that generally speaking, almost any point will work to show that the type of functions we will be dealing with are nonlinear, if that is the case. So we can just let s and t just be equal to 1. Okay, so if we do this, that trick will generally work. If it doesn't work, then relax that assumption and then try to find a counterexample there. So from here, I'm just going to assume that these things are 1, and I'm going to focus on these vectors. Okay, so question. What terms up here look bad? So if I'm trying to find a counterexample, it's kind of a good idea to have an idea of how I'm going to construct the counterexample. So if I just look up here, we can say, hey, this y times z term, that doesn't look particularly linear. So let's just try to use this to break it. So here, the point that I picked was just f of 1, 1, 2, and I evaluated this thing to compute this term over here in green, this term here. Okay, so if I do this, straightforward computation, y is just 1, so this is a 1, X is just going to be a 1 from here, so this will just be a 1. And y times z, well, that's 1 times 2, so I get 1, 1, 2. Okay, on the other side, I need to come up with these two f of x and f of y vectors. That means I need to figure out what x and y are going to be given this point. And again, there's infinitely many ways that I can do this. And I just chose to decompose 1, 1, 2 as 1, 1, 1 plus 0, 0, 1. Again, that's a choice. There's other ways that you can do this. So from here, I now want to evaluate f at these 2 points, and then I want to show that the sum that I get on this right-hand side is different than what I got on the left-hand side over here. Okay, so straightforward computations. If I plug in 1, 1, 1 and 0, 0, 1 in for x, y, and z respectively, I get 1, 1, 1 plus 1, 1, 0. That's just 1, 1, 1. This is not the same thing as what I found for f of 1, 1, 2. Therefore, this would be my counterexample that this is not linear. So again, you could do other cases, like I could say f of 0, 0, 0. This is just going to be 0, 0, 0. And then I could try to decompose this to be, say, f of, let's just say 0, 1, 1. And then for the other bit, we'll say that's f of 0, negative 1, negative 1, right? If I take 1, 1, 1, or 0, 1, 1, and add to that 0, negative 1, negative 1, I do get 0, 0, 0. But if I evaluate the function, well, here, the first term would be y. Y is equal to 1, so I get a 1. The next term is x. X is 0, so I get a 0. And then I get a y times z, so I get a 1, 1, which is just, or 1 times 1, which gives me 1. On the other side, over here, my y is now negative 1, so I get a negative 1. My x is still 0, so I get a 0, and then I get negative 1 times negative 1, which is positive 1. And if I add these together, the first component's 0, that's good. The second component's 0, that's good. The third component's 2. This is not the same as this point up here. Therefore, that would be another counterexample for this being nonlinear. And I literally just came up with this way of splitting it up on the fly. So literally any point will pretty much work. Okay, let's look at one more example. Prove that this thing is nonlinear. So pretty clearly, x squared is the term that doesn't look linear. So let's try to break it. So basic idea here is you could say, hey, 2 squared is 4, right? And 2 is equal to 1 plus 1. But 1 squared plus 1 squared is 2. This is not equal to 4. So that's kind of my motivation of how I found the point to break this. So from here, you could just say, hey, let's do f of 2 comma 1. Again, I just picked 1 for y. Any number works here. So f of 2 comma 1, that's pretty clearly the point 1, 4, right? The discussion we had here, 2 squared is 4. On the other hand, this point 2, 1 can be split up in this way, where I have a 1, 1 plus the 1, 0. And from here, if I evaluate f at these 2 points, I simply get 1, 1 for the first one, 0, 1 for the second one, which is 1, 2, which obviously is different than 1, 4. So from here, that would be a counterexample for this being linear. Okay, so beyond here, we can now talk about how to visualize matrix multiplication. Just since we've done stuff with it for a while, we've talked about these linear transforms, and it's kind of a good spot to talk about visually what's happening. So here, I'm just letting T and L be 2 linear transforms with these given standard matrices. These matrices were just chosen because that's what I used in the picture, and it was pretty randomly picked. So let's examine what this does geometrically. So L, so given a vector x in R2, L outputs another vector in R2. Now vectors only have 2 kind of defining properties, if you will. They have a length and they have an angle or a direction. So if L as a linear transform is going to take x and map it to something, it could either have the same length or a different length, or it could have the same direction or a different direction. So from here you can see, if I take the point on this unit circle here, this particular value of x gets mapped to this L of x. So now let's just notice something. If I wanted to compute L at, say, any other scalar multiple of s, so let's just say TS, TX, this is the same thing as T L of x, right? So if I scale this all I do is scale the vector here. So it's actually sufficient just to look at vectors on the unit circle, and that will let me know what L does to everything since L is linear. Okay, so with this kind of in mind, let's look at another point. Well, if I pick a different vector here, then L of x just gets mapped to a different vector over here. So I can do this for all the points on the unit circle, and you can notice that if I take all of the vectors on the unit circle and I look at what they get mapped to, then this kind of outline of this unit circle gets mapped to this outline of the ellipse. And here, this dotted circle here is the unit circle just for reference. So really what's happening is vectors that lie on the unit circle get mapped to vectors that lie on this ellipse. In general, that's what all linear transforms do visually. It could be the case where L evaluated at all of these vectors along here doesn't actually get mapped to a full ellipse, but it could just get mapped to a kind of degenerate ellipse where one of these kind of defining lengths is equal to 0. And by defining lengths, I mean you can define an ellipse by this direction here and this length here. One of those lengths could be 0. Okay, so beyond there, T is another linear transform, so I could look at what it does. So for any given L of x over here, T just gets mapped to a new vector, T of L of x, which again just changes its length and its angle. So from here, you can tell that this little ellipse here gets mapped to this little ellipse here. And by saying the ellipses get mapped, I'm really just using slang for saying all of the vectors that lie on that ellipse would then get mapped to a vector that lies on this new ellipse. Okay, so under kind of the guise of all of this stuff going on from here, we can examine what function composition or matrix multiplication equivalently do geometrically. So if I have my T times L or T of L, I first take my vector x and I map it to whatever it gets mapped to by L. So this thing could get mapped over here. And then I apply T. So geometrically, matrix multiplication is really just do this transform and then this transform. And kind of pretty obviously, the order in which I do those transforms could matter. Not always, but sometimes it can. Okay, so that's it for this visualization here. As I've said in class, you should have access to this little applet, and you can play with it on your own if you want. Okay, let's talk about Markov chains. So here to discuss Markov chains, I'm just going to give a kind of more realistic example where you could actually use this and for a real world problem. So in Siet, Morocco, the first local transmission of COVID-19 was on this date. We want to try to predict how things will spread. Okay, so from here we go and collect some data, and we find that on any given day, the probability of a healthy person becoming an active case is given by this, the probability of an active case recovering is given by this, and the probability that someone who was an active case dies the next day is given by 0.01. Okay, so we want to set up a stochastic matrix for a Markov chain to model the COVID-19 pandemic in this city. And then we want to use my stochastic matrix to compute the number of active cases on day 2, assuming that there are 16 active cases, 1 death, and 1 recovered, and a population of 10,000 on day 1. And also kind of implicitly, the population isn't changing. So again, I mentioned this in class, but this is actually part of a paper. So if I pull this up, there we go. So if I pull this up here, you can see here's the paper. It's pretty short and to the point. Handful of references. Could be useful to look at if you're interested in examining it in a little bit more detail. Okay, so how do I go about doing this? Well, the first thing I need to do is I need to think of what states people are in. So I could build a table with, say, like, oh, I have healthy people, blah, on day 1, stuff on day 2. But you can also do this using a graph. And I find the visual representation a bit nicer. So here I can be in a healthy state. I could also say have COVID. So we'll call that the A state. I could have had COVID and recovered. And I could have passed away or died from COVID-19. Okay, so these are my only states within this model. Better models, you could add more states. So now I really need to figure out what transmissions happen where. Well, if I'm healthy, two things can happen within this model. I could become an active case, and if I became an active case, this is the probability that I would become an active case. So here this number tells me the probability going this way. It's not like the directed graphs for flow where that tells me the flow, right? The number of people who move here will change as the number of people in H changes because I multiply H by this thing. Okay, so now I could say healthy people could say go into like pass away, but within this model, we're not going to do that. We'll just say that healthy people stay healthy. So the probability that a healthy person stays healthy, well, since the only options are I stay healthy or I get sick, this probability will simply be 1 minus the probability that I get COVID the next day. Or if you work this out, that's just 0.998. So that's the number that goes here. Okay, so beyond here, let's look at affected. If I have COVID, I could recover, and I know what the probability of that is. It's just this 0.23. I could pass away, and I know that probability is 0.01, or I could stay an active case, so 0.76, simply 1 minus this number minus that number. Okay, now if I'm recovered from COVID, here I'm just assuming that I can't get COVID again. This is a decent model for the kind of time spans that they're used here, but you could improve upon the model by allowing recovered people to become reinfected, which you would really want to write down as a different affected node up here, just because after you get COVID and you recover from it, the probability of maybe recovering again or dying could be different than the first time you get COVID. Okay, so that's one way to generalize the model. And here, if you're dead, you stayed in a dead state. You no longer, So this is kind of my directed graph version of what's happening here. So if I just kind of draw it up here, that's this picture. So beyond here, I want to convert from a directed graph into a stochastic matrix. So I know my matrix is going to be something like this. Okay, so I'm going to label the columns my healthy, active case, recovered, and dead, and the same thing here. So now we have to figure out how we put these numbers into this chart. Well, the numbers that go here will be what's happening on day 1, and then over here we're saying if the next day occurs, what's the probability that I change state? So if I'm healthy on day 1, what's the probability that I'm still healthy on day 2? Well, that's just this number here. So this will be 0.998. If I'm healthy on day 1, what's the probability that I'm an active case on day 2? 0.002. And I'm assuming I can't recover from COVID if I've never gotten it, and I can't die if I don't get COVID within this model. So do the same thing for A, R, and D. So just for A, I can't become in a healthy state again. I become recovered, but I could be sick the next day, so 0.76. I could recover, 0.23, or I could pass away, 0.01. And you can do the same thing here, so 0010, 0001. Okay, so there's the matrix in slide form, but yeah. Okay, so beyond here, I now want to use this stochastic matrix to make predictions, right? So this was the data that I was given, right? On day 1, I had 16 active cases, 1 death, 1 recovered in a population of 10,000. So I need to find the state vector for day 1. So how do I find the state vector for day 1? Well, the state vector will just be a bunch of percentages of people in each one of these states, and those percents need to add up to 1 for this to be a stochastic vector. Okay, so from here, how do I find these percents? Well, I want to know the percent of people that are healthy, right? So if I put the total number of people that are healthy here, say 100,000 minus the people who are sick, 16 active cases, 1 case, or 1 death, 1 recovered, so minus 18, then this would just be a raw number, right? But I want this to be a percentage. So if I just really quickly did this for the rest of them, 16 active cases, these are all numbers. So to turn this into a percent, I divide by the population. So that's what I get here. Okay, so beyond this, the next question is, how do I get x2? Well, x2 would simply be the stochastic vector that tells me what's happening in the system multiplied by x1. Okay, in general, xn is simply going to be the matrix A, if I call this thing A, times x sub n minus 1. Okay, so from here, you can actually clean this up a little bit, and you can notice this is just A to the n minus 1 times x sub 1. So there's an application of vector or matrix multiplication for you. So from here, that's what my x2 is, but I want to figure out how many active cases I have on day 2. So if I multiply this all out, I can take the second component, the second term in the product, to figure out what percent of people are active cases, but I need to convert that to a raw number of people, so I just multiply by the population. Okay, so from here, if you do the math, this is 26.06 or 26 people. Okay, so oftentimes we show you applications like this and they're kind of contrived. This one came from the paper, so we can examine the results briefly. So here are these different plots. The red is the modeling the number of people who have died. Blue is active cases. Green is the number of recovered cases, and black is total. So here, these numbers that I have in this chart are fuzzy, right? Like these numbers aren't exact, pure values. Things can change, right? So because of that, if you want to actually account for the variance to get an idea of how good your model actually is, what you want to do is you want to run this bunch of simulations with different values other than these raw values that I picked here. Okay, so if you do this and you run this simulation with different possible values here that lie within the statistical range, you get a range of possible outputs. So here, that's what these lines represent. Those are just the variations that you can get, and the solid curve here is just the average. So these dots actually are the real world data. So you can notice that the dots match really well with the curve up until around here, around this point over here, where they changed their COVID rules. So this is a decent model. And yeah, these type of models can be quite useful. Just a word on how to generalize this to make it even better than this model, and a brief discussion of how government COVID models actually work. Instead of using this number, you can come up with an equation for this. You could say, hey, the percent of people who would become affected isn't going to be just a fixed number. It's going to depend on a few things. So you could say, hey, it's a function of, say, the number of healthy people, or the number of people who have COVID, or the number of people who recovered. Because if you have some people who've recovered, that lowers the probability that you'll have an interaction from a healthy person and a sick person to spread the disease. You can also add other things in here, such as government measures and all of this stuff, and it does become quite complex, but that's how to generalize this to actually do some real-world modeling with this kind of toy model here. Okay, let's change topic and talk about computing inverses of matrices. Okay, so sometimes we know matrices are invertible. So a natural question is, how can I find the inverse in a clean, concise manner? Well, it turns out that if you just say, hey, let X be the inverse of this matrix, if it exists, it might not exist, that's fine. But if X is the inverse of this matrix, then I know that A times X has to be the identity matrix of the appropriate size. So explicitly, the identity matrix will be A times X. But this X has this form, but this X can be written as these column vectors, right? So if I want to take A times X, that's the same thing as taking A times each one of these column vectors. So now I have matrix, the identity matrix, is equal to this matrix here, where the column vectors are these AX1, AX2, AX3. If two matrices are equal, then their components are equal. In particular, this means that the column vectors will be equal as well. So this thing has to be equal to this. So from here, I can write this as a system of three equations. Explicitly, this column vector is equal to this column vector is equal to this column vector, and this column vector is equal to this column vector. Okay, so now I ultimately want to solve this system, And I really don't want to go through and take my A and augment it with each one of these E sub i's and solve this 3 times for this case. In particular, if this was a really big matrix, say 5,000 by 5,000, I don't want to solve 5,000 systems. So a way I can systematically make this a little bit easier is to triple augment a matrix and solve for each one of these vectors all at once. So explicitly what I'm doing with that is I'm simply taking this and plugging in my E1 vector, and then I'm plugging my E2 vector, and then I'm plugging in my E3 vector. And I'm solving this by row reducing A, and then I'll just interpret the results for one of these terms at a time. So like interpret the augmented matrix with this term being there, and then maybe do it with the term in orange, and then do it with the term in green. So this is a very useful technique for solving multiple systems of equations at once, given that you're using the same coefficient matrix A. Okay, so explicitly I want to row reduce this, or if I use my matrix A over here, this thing. We all know how to row reduce. This thing row reduces to here. Okay, so now I've shown that this thing row reduces to the identity matrix with some vectors that I'll just call V1, V2, and V3. So the interpretation that I had before as a system of equations is still true. That hasn't changed at all, right? So since that interpretation still holds, I can reuse that to turn this augmented matrix here into 3 systems of equations again. So explicitly, I'd get my matrix times x1 vector is equal to the v1 vector. And then the next one, I'd get my matrix times the x2 vector, and that will be equal to the v2 vector. And finally, I get the same thing for the v3 vector. So just for completion, this thing here. So while I write this down, just notice that from here, I times any vector is just the vector that I started out with, right? So this I times x1 is just the same thing as x1. So really, the 3 systems of equations are x1 is equal to the first column vector, x2 is the second column vector, and x3 is the third column vector. Okay, my goal was to know what x1, x2, x3 are. I now know what they are. So since x was A inverse, I can now conclude that A inverse is the matrix where this thing goes in the first column, this thing goes in the second column, and this vector here goes into this third column. But notice something really nice. This is exactly the same thing as this, right? So in general, since this is just equal to this, I can conclude that I can build an algorithm out of this to solve for an inverse. I take my matrix A, take the identity matrix of the same side, and augment a system like this. I row reduce, and if this is the identity matrix, then my system of equations will just be this thing. Therefore, the matrix inverse would just be this term here. Okay, so in practice, just throw them in, row reduce, pull it up, given that this becomes the identity matrix. So this begs the question, what happens when that does not simplify to the identity matrix? So let's try this. If I plug this in, I get this thing to start with, I row reduce it, and I find out that it turns into this. This is a problem. If I just examine the first system of equations that I'd get from this augmented system, very clearly this is an inconsistent system. This means that there is no solution for my vector x1. Similarly, there's no solution for x2 or x3. Okay, so that's kind of bad. Beyond this, if you want to use higher order reasoning to determine that this is not invertible, since this was not the identity matrix, you can say, hey, the rank of A is 2, right? A is just this thing here, so if I row reduced it, I would get this. And here, there's only 2 columns that have a leading 1 in it. On the other hand, the rank of the 3 by 3 identity matrix is just going to be 3, right? That's pretty straightforward. And we have this nice theorem, 30.4, that states that A is invertible if and only if it has the same rank as the identity matrix of the same size as A. So from here, the ranks aren't equal, therefore A is not invertible. You kind of have your choice of explanation here of why this is not invertible, but it's kind of good to use the higher order things. And it's still also good to be able to interpret this as systems of equations so that you actually know what you're doing. Okay, so for the last example, we're going to talk about solving matrix equations. So in general, you often end up with an expression like AX is equal to B. Okay, and it's often nice to solve this expression for multiple values of B. So if A is not invertible, you're kind of stuck doing a little bit of work there. But if A is invertible, then things are nice. So let's solve this thing for these 4 values of B. So we could do this one system at a time, right? I could do A and augment it with each one of these vectors B sub I, for I is 1 all the way up to 4. That's a bit annoying in terms of my computations I'd have to do. I could also do this by quadruple augmenting with, say, B1, B2, B3, and B4, and then I could solve this if I wanted. But then if someone then later comes around and says, hey, can you do B5? You have to resolve the system, right? That's a bit annoying. So what I could do instead is I could try to find the inverse of A if it exists, and then I could try to solve this by undoing A. So let's first try to find the inverse, because if we can't find an inverse, then we can't use this technique. Well, I take it, I write my A, augment it with the identity matrix, 2 by 2, since A was 2 by 2. I row reduce this. Lo and behold, this is the identity matrix here. Therefore, I can read off and say, hey, I have this inverse here. So let's try to use this A inverse to solve this for the various values of A, various values of B. So from here, you can notice if A is invertible, then I could just take this equation here, and I could multiply both sides by A inverse, right? I could take this thing and multiply both sides by A inverse. So here I would get A inverse on this side, and over here, give myself a bit more space. There, I get A inverse over here. Sorry for the messing up with the things. My mouse needs to be replaced. Okay, so from here, this A times A inverse of X, I know that's the same thing as A inverse times A, in parentheses around here, times X. Okay, so I know this is equal to this A inverse B. So from here, A inverse times A, well, that's just the identity matrix. And identity matrix times X, that is just X. So if I clean this up and put my equalities on the other side, then I get this string of inequalities or equalities that allows me to solve for X just by multiplying by the inverse of A. So notice here, I'm not dividing. You can't divide by a matrix, but you can multiply by the inverse on, say, the left-hand side or the right-hand side. Okay, so if I do this in practice, all I have to do is take this matrix A, this or A inverse, this thing here, multiply it by B, and if B is this 1, 0, then X is minus 1, 2. Same thing here. I just take this 0, 1, multiply it by A, and get that. Same thing for all of these. Pretty straightforward. This is part of the reason why we really care about these inverses, when we can get them. Okay, so beyond that, yeah, do look at the online tutorial questions. There's quite a few nice ones this week, so check those out. And here we have a little educational meme. So if A is a n by n invertible matrix, there's an error in the meme that I grabbed, then all of these other things are also true. Like everything's equivalent. So if A is n by n invertible matrix, then the rank of the matrix A is n, right? Just if I take the matrix A and try to row reduce it, I know I get the identity matrix, so I'm good. The null space of A only contains the 0 vector. Well, if I try to compute the null space, the only solution will be 0. The transpose of the matrix A is invertible. Well, if I transpose it, then nothing will really change, right? I just swapped the rows and the columns, and all of the rows had a leading 1 in it, so yeah. The RREF of A is the n by n identity matrix. Well, yeah, that's equivalent to all of these other things. and the determinant of A is non-zero, well, that is a nice way to quantify when matrices are invertible or not, and we will talk about that next week.